Welcome back again. In today's lesson, we're going to continue talking about altering product strength of pharmaceutical products. But whereas a previous lesson talked about diluting products with a pure diluent, in this lesson we're going to talk about enhancing the strength of a product, either using pure drug or another concentration of drug by mixing two partially concentrated drugs together to end up with a final concentration that's somewhere in between. Now, as a review, when we talked about product dilutions, we talked about an equation, C1Q1 equals CQ2Q, or rather the first in concentration multiplied by the first quantity equals the second concentration multiplied by the second quantity. And that concept does work very, very well if you're using pure diluent that doesn't have any concentration to itself. This would be something like pure water or an ointment base. But sometimes the equation is really more like this. I'm going to call it C1A and Q1A and C1B and Q1B, meaning that you actually have two different products contributing to that first quantity and concentration in order to get to your third. And so if you're good at algebra, this really isn't a big deal, but if you're not good at algebraic equations, there are other ways to solve these problems, and so we're going to cover those in this tutorial. So let's look at an example here, and this is saying how many grams of pure coal tar. So the first thing you need to know is if it's saying pure anything, that means it's a 100% product. So how many grams of pure coal tar should be added to 36 grams of 4% to make a 10% ointment? So let's start with what we want. So on our equals side, we want a 10% ointment. And that's all we know. We're going to solve for how many grams is that. Well, what do we have to start with? Well, we know that we have a 4% product, that's 36 grams, and we know that we're going to be adding to that an unknown amount of product, that's 100%. That means on our final side of our equation, our final weight is actually 36 plus X grams. And so again, if you write this out in a proper way now, that's algebraic, I'll change to blue. So the way this would look in a true algebra equation, and if we're adjusting for the fact that we want to make sure we convert our 4% to what it really means, then our final algebra equation here is going to look something like this. And forgive me while I write. And then you would have to solve for X. So if you're good at algebra and if you solve for X here, then X is 2.4 grams. But if that's hard for you to follow, there is another way to do the problem. And that other way is using what's called the alligation alternate. And this is basically a more visual representation of mixing together products or strengthening products that allows you to not have to use algebra. The way you set these up is whatever your desired final concentration is, that's going to go into your middle. And then visually, you're going to put the concentrations of the two components you're mixing up to the left and down to the upper left and the lower left of that desired final. And then you literally subtract across, and the difference between those concentrations becomes the parts of the components that will be in the final product. Once you figure out the number of parts, you can solve for actual values. So this probably sounds and looks really, really confusing right now, but let me show you this with a concrete example. We're going to go back to our coal tar. Let's go with the concentration we want to make. We want to make a 10% product, so we're going to put 10% in the middle. Now, we have two products that's coming from. We have a 4% product here, and we have a 100% product. So if we subtract, and you can use all positive numbers, 100 minus 10 is 90, 10 minus 4 is 6. So what this 90 and the 6 means is this means that in your final product, it's going to be 90 parts 4% and 6 parts 100% for a total of 96 parts. Then, using the numbers we have, we can solve. So we want to solve for the amount of the 100% solution, or the 100% product, and that's representing 6 parts. So we can set up a simple ratio to say, well, how many grams is 6 parts if we know that 36 grams was 90 parts. And then when you solve for x, you're going to find that you once again get 2.4 grams, the exact same answer that we got when we did it using algebra. So let's look at two more examples showing how the equation would be set up algebraically as well as how it would be solved using alligation alternate. This next one, we're asking for how many grams of a 2.5% cream should be mixed with 360 grams of a 0.25% cream to make a 1%. So if we're going to set this up using algebra, and I'll do this one in blue, we're solving for x grams of our 2.5% cream. We're adding to that 360 grams of our 0.25% cream. I'm running out of room to write my units, but you would want to do, and that would equal what we're making. So what we're making, the final weight, is going to be 360 plus x grams times we're wanting to get to a 1% cream, which would be 1 over 100. Again, I'm running out of space. So you can set up this algebraic equation and you can solve for x equals 180 grams. Now, I'm going to clear this and show you how you would do the same problem using dimensional analysis. So remember, when we did this with algebra, we got an answer of 180 grams. So that's what we're aiming. So how do we do this with dimensional analysis? Well, what strength do we want? That goes in the middle. And I said dimensional analysis. I meant alligation alternate. I'm sorry. But what we want is a 1% product. So that goes in the middle. What are our source products? Well, we have a 2.5% product and a 0.25% product. So if we do 2.5 minus 1, we know that there are 1.5 parts, and those are the parts of what is on the same horizontal lines. That's 1.5 parts of the 0.25% product. If we do 1 minus 0.25, we get that there are 0.75 parts of the 2.5% product. And again, if we wanted to know what our total parts were, let's say I'll use black for this, the total parts would be 1.5 plus 0.75, which is 2.25 parts. Although that's not going to be necessary in this problem, because we're going to plug in what our knowns are. So we're solving, and we're solving for how many grams of the 2.5%. So we're solving for this portion. So we're solving for x grams over 0.75 parts is equivalent to what is our other known? Well, we know exactly the weight that's represented for these 1.5 parts. So we know that that weight per our problem was 360 grams. So that's 360 grams represents 1.5 parts. And so again, if you solve for x, you're going to see that we get the exact same solution, 180 grams. So let's go ahead and look at one final example. Again, if we're going to set this up using algebra, I'm just going to go ahead and write out what this equation means. We're asking for how many milliliters of a 50% solution. To try to have room, I'm not going to put my units here, but you really should. But if we have a 50% solution, and we're solving for x grams, we want to know how much of that, when combined with a 5% solution, also of an unknown, so I'm going to hold off here, equals 4,500 milliliters of a 10% solution. Well, if we know our final is 4,500 milliliters, then the volume here must be 4,500 minus x. So again, this is how you would set up this equation if you're good with algebra. And when you solve, you would solve for x equals 500, which would then mean that your 50% solution is 500 milliliters, but your 5% solution would actually be 4,000 milliliters. Okay, Let's see how this works again using dimensional, or not using dimensional analysis, using alligation alternate. I don't know why I keep saying dimensional analysis. So using our alligation alternate, we want a 10% solution. We're starting with a 50%, and we're also starting with a 5%. So again, if we do our subtraction, this means we have 40 parts of the 55, or the 5% solution rather, and we have 5 parts of the 50% solution for a total of 45 parts. Now, what's the other known? In this case, the other known is the total volume. So we know that 4,500 milliliters represents 45 parts. And then we can set up our equations to first solve for the 50%. That would be an unknown number of milliliters for 5 parts, or that would equal an unknown number of milliliters for 40 parts. And when you solve for x in these cases, you'll see that you'll once again discover that it would be 500 milliliters of 50% solution and 4,000 milliliters of 5% solution. So, sort of to conclude, just remember that if you're diluting with pure diluent, which means it's concentration less, so this would be an ointment base, sterile water for injection, something like that, it's the simple C1Q1 equals CQ2Q. If you are enhancing strength, either by adding a 100% product or by mixing 2 products together, then you can still use that equation, but it turns into a slightly more advanced algebraic equation, or if it's easier for you to work through it, you can use the alligation method. So with that in mind, I hope this gives you enough of an idea of how to move forward to go ahead and practice some problems, and please let me know if you have any trouble.